Hello, boys and girls. We are entering chapter 6. It's very exciting. We are going into fractions now, which is awesome. You're like full-grown adults now working on these wonderful fraction things here, aren't you? Okay, so lesson 1 in chapter 6 is all about equivalent fractions. Okay, so equivalent, you kind of hear equi, right? Like equal. So they're fractions that are worth the same amount, but they're just written in different ways. Okay, so let's look at number 2. It says use the model to write an equivalent fraction. All right, well, let's look at this. This is 3/4. Now I'm looking at the model and I see shaded 1, 2, 3. 3 rows are shaded. There's our numerator. Out of 4 rows that make the whole. The 4 is our denominator. Okay, so I see why, let me do some reshading. I see why that model shows 3/4. Okay, so now we have the same model, but we are going to change it and make an equivalent fraction. So let me see now. I'm going to draw another line. Let's see. Okay, I drew that right down the middle of the rectangle. So now, let me make sure it's down the middle. 1, 2, 3, 4, 5, 6 on that side. 1, 2, 3, 4, 5, 6. Yes, it was exactly down the middle of the rectangle. Okay, so I really just made more pieces. I made more pieces. It's like the brownie problem you did in class today. So over here, 4 rows made the whole. And in this one, since I cut it right there, we have more than 4 rows that make the whole. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 rows make the whole thing. And that's what the denominator's job is. The denominator is just to tell us, hey, this is how many pieces makes the whole thing. That's the only thing the denominator does for us, okay, in fraction land. So how many of these are shaded? 1, 2, 3, 4, 5, 6. So 6 out of the 8 rows are shaded. And it's really the exact same amount as this problem, isn't it? 3 out of 4 rows is equivalent to 6 out of the 8. Okay? Because I cut it in half. It's not just 4 rows anymore. I chopped it right there. So let's call it pieces instead of rows. So I want you to notice something, guys, okay? The denominator doubled, didn't it? I made twice as many pieces to make a whole thing because I just cut it in half. But look, the pieces aren't the same size, are they? They're much smaller. So that piece is much smaller than that piece, isn't it? Okay, so I doubled the number of pieces, but the pieces are smaller. So if I doubled the number of pieces, that also doubled the number of pieces that are shaded because it's equivalent. We didn't change how many are shaded gray. We just cut them in half and made them smaller. There are more of them in the whole, so there are more of them shaded now. Okay? All right, let's go on. All right, guys, so now we don't have models to look at. So we're just going to look at these fractions and let's start here with number 3. 8/10 compared to 4/5. Are they equivalent? Well, let's do this one with a model, okay? So we have to make 10 equal parts here. So, oops, I'm going to make that white. 1, 2, 3, 4. So let's check if I made 10 equal parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So how many parts do I have to shade? I have to shade 8. I have to shade 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So we're comparing that to 4/5. Now, fifths, well, that's half of 10, isn't it? So I have to make half as many pieces in this thing. So 1 piece, remember I'm trying to make 5. 2 pieces, 3 pieces, 4 pieces, 5 pieces. So now I've made bigger pieces, but I don't have as many. I have 5 pieces, but the pieces are a greater size. Let's shade 4 of those greater size pieces. 1, 2, 3, 4. So 8/10 is equivalent to 4/5. So if I divide the number of pieces in the whole by 2 to get 5, and I divide the number of shaded pieces by 2 and get 4, those are equivalent fractions. I divided the number in the whole thing by 2, so then of course the number shaded has to also be divided by 2. Okay? And if that wasn't 4, these would not be equivalent fractions, would they? All right, let's check number 4 now. 1/2 compared to 7/12. Well, you guys know a lot about 1/2, don't you? So let's look at this, see if we can think about this without using a model. 2 pieces that make the whole and 12 pieces that make the whole. Okay, but we still have, just think about, we still have the same candy bar, but we either break it into 2 equal parts or into 12 equal parts. Okay, so here's half. I know I said I wasn't going to use a model, but I have a model here anyway. Okay, so there's 1/2 right there. Okay, that's the first fraction. Let's see how that compares to 7/12. If I have 2 pieces that make the whole, I can divide that by 6. Oh my gosh, not divide it by 6. Multiply it by 6. Good night. I can multiply it by 6 to get 12 pieces. So I'll have the same candy bar, but instead of separating into 2 equal parts, I'm going to separate it into 12 equal parts. The pieces will not be as big, will they? But I'll have more of them. So let's see. If I do 2 times 6 to get 12, can I do 1 times 6? Because that's what I'm going to be doing to the pieces. Is 1 times 6 7? No way. Nope. And now let's do it on the model, okay? All right. So now I've divided the candy bar into 12 equal parts. Let's shade 7. So do you see what I was talking about? The parts are, there are more of them, but they're much smaller. So is 1/2, which is this, equivalent to 7/12, which is 1, 2, 3, 4, 5, 6, 7? No, it is not. 7/12 is more, so these are beep, beep, not equal. Okay? Let's look down here at number 7. Now, do you guys remember using benchmark fractions in 3rd grade? This is a perfect one for benchmark fractions. Okay, a benchmark fraction is, remember, like a super important one, like 1/2 and 3/4 and 1/4. All right. So if you have something with 8 pieces, what's half of 8? Half of 8 is 4. So 4/8 would be exactly half, but we have 5/8. So we have one extra piece, don't we? We have more than half on this side. Now let's think about 4/10. All right, so in this fraction, we have 10 pieces that make the whole thing. What's half of 10? Half of 10 is 5. So 5/10 is half. And what do we have in this fraction? Well, we only have 4. So we have 1 less than half. So 5/8 is 1 more than half. 4/10, 1 less than half. These are not equivalent fractions either. All right, let's look at number 8. 2/6 compared to 4/12. Okay. Now if I look at these denominators, I know that they have doubled the number of pieces. 6 times 2 is 12. So they've doubled the number of pieces that makes the whole thing. You can actually use this model, right? Because that has 12 equal parts. So if I double the number of parts that make the whole, the number of parts that I have shaded should also be double. So let's check. Is 2 pieces times 2 4? Yes, it is. So just to prove it, since I have this handy dandy model up here, here are, I'm going to shade them white, 2/6, 1, 2, right? And then the 4/12, I'll put, let's use black, 1, 2, 3, 4. Equivalent. Ring-a-ding-ding. You guys are going to get so good at doing this, okay? It's good to start out thinking about models and all that stuff, but you guys are going to be like experts in this. All right, let's keep going. This is number 12 at the bottom of the page, okay, about Sophia's vegetable garden. I wish I had a vegetable garden. I do not. Sophia's vegetable garden is divided into 12 equal sections. She plants carrots in 8 of the sections. Write 2 fractions that are equivalent to the part of Sophia's garden that is planted with carrots. All right, let's do a model of the garden. Why not? Okay. It's always good with fractions to see. It has 12 equal sections. 1, ding, 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 ding. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let me see here. She plants carrots in 8 of the sections. I'm going to put a C in 8 sections. C for, oh, you cannot read that, can you? C, 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 C for carrot, C, C. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have to write two fractions that are equivalent to the part of Sophia's garden that is planted with carrots. Well, the first fraction I write, let's start with the one that's right in our face, right? How many pieces are shaded? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of how many that make the whole garden? Remember the job of the denominator. How many pieces make the whole thing? It says it right there, right? 12. 12 equal sections. Okay? So if you want, you can think about something maybe that you can divide 12 by and 8 by. That's the same, but let's look at the model, okay? I'm going to separate these 12 sections into 6, okay? So the green are new sections. 1, 2, 3, 4, 5, 6. So now I have 6 equal parts instead of 12 equal parts. Okay, I made the sections bigger. So I'm going to put right off the bat a 6 for my new denominator because I just changed the garden into 12 from 12 equal sections to 6 equal sections. So let's check the carrots. How many sections of my new garden separation have carrots? This one section does. 2, 3, 4. You see that? 4 out of the 6 sections have carrots. So let's think about what we were talking about earlier. I divided 12 by 2, right? I gave each 2, okay? And I got 6 sections. So if I divided the number of sections by 2, I should be able to divide the number of shaded parts by 2 and get 4. 1, 2, 3, 4. Okay? Beautiful. Well, this is kind of a pretty colorful slide. All right, let's keep going. Now we are on the back. Let's see what Jeff's doing here. Jeff uses 3/5 size strips to model 3/5. He wants to use 1/10 size strips to model an equivalent fraction. How many 1/10 size strips will he need? So let me reread. You know we need to reread all the time here. What does Jeff have? He has 3/5 size strips to model 3/5. You know what this reminds me of? Our fraction bars, right? So he has, let's just think about that. He has 3 pieces that are each worth 1/5. Okay? Doesn't that remind you of fraction bars? 3/5 size strips, and he is modeling 3/5. 1, 2, 3/5. Okay? He wants to use 1/10 size strips to model an equivalent fraction. So he wants to use 1/10 size strips. He wants to go from 3/5 to 1/10 size. So there's 1/10 in our denominator. Okay? I want you to think about this. Think about this. Okay? what are we going to do to the 5th size pieces to get to tenths? Yeah, we're going to multiply them by 2. So each of these 1/5 is going to be a 1/10 and another 1/10. Okay, we doubled 5 to get our tenths. So, oh, these are not equal pieces, are they, guys? Sorry about that. Just use your imagination. These are all equal. No, they're not. Okay, so we doubled the number of pieces that make the whole thing because Jeff's using 10th size strips. So since we doubled the number down here, what are we going to do up here? Double that also. Okay? What's 3 times 2? 6. And let's go over here. 1, 2, 3, 4, 5, 6. Okay? So how many 10th size strips will he need in order to have the equal or equivalent amount to 3/5? He will need 6 10th size strips. All right? Beautiful. Let's go to the next one. All right, we're down here at review from Chapter 5, Lesson 5. It says 4 students each made a list of prime numbers. Do you remember what prime numbers are? Remember? Okay, let's see. Eric has a list. Maya, Bella, Jordan. And it says, who made an error? An error is a mistake. And included a composite number. Oh, now we have another word to remember here. What's prime and what's composite? I know you guys remember, right? A prime number only has 1 and itself as factors. Okay? Can you think of an example of a prime number? 5. Yeah, great job. Right? 1 times 5 equals 5. You cannot multiply 2 whole numbers other than 1 and 5 to get 5. 5 is a prime number. And then a composite number, that's every other number that's not prime, every other whole number. So let's take a look at their lists. You know what I'm going to do? You guys, we know lots of prime numbers already, don't we? So I know 5's prime. I know 7 is prime. 3 is prime. There's 5 again. There's 3 again. Oh, there's 2. 2 is the only even prime number. 7, that's definitely a prime. So we knocked those off right away. So far, no one's made a mistake. Oh, I know 13 is prime. What about 17, boys and girls? 17. 1 times 17. Let's see, 2 times nothing. No. How about 3? 3, 6, 9, 12, 15, 18. Oh, wait, you know what? 17 is prime, isn't it? There's only 1 times 17. Oh, and there's 11 down there. Is 11 prime? 2 times nothing is 11. 3, 6, 9, 12. No. 4, 8, 12. No. You know 11 is prime. And we just talked about 13. So let's see what we have left here. 23, 19, and 21. Is there anything screaming out at you? Well, I bet there is. Do you remember the divisibility rules? Yeah, we can't use the rule for 2 because none of these have 0, 2, 4, 6, 8 in the ones place. So that one doesn't work. What about the divisibility rule for 3? Remember, add the digits and see if the sum is divisible by 3. So that would be 2 plus 3 equals 5. Is 5 divisible by 3? Nope. Then 23 is not. 1 plus 9 equals 10. Is 10 divisible by 3? Nope. Then neither is 19. So 21. 2 plus 1 equals 3. Is 3 divisible by 3? 3 is divisible by 3. 3 divided by 3 is 1. Okay? So, ring-a-ding-ding, 21, you are not a prime number. Because I know that 3 times something is 21 because we just saw that it's divisible by 3. So what is it? It's 3 times, of course, 3 times 7. And then 1 times 21. So 21 actually has 4 factors. So who made an error? Who was that? Jordan. Oh, Jordan. That's all right, Jordan. You'll get it next time. All right, guys. Excellent work. We are going to destroy it on fractions in this chapter. So take a deep breath and get ready. Have a good night.